Kalimera solus kai kalos irta testo oikonomika demos kratos. Hello everybody and welcome to Oikonomika, all about economics and finance. So very happy to be with you all today. I hope you will be watching my video. Thumbs up if you are new around here. Subscribe to my channel. There is a wealth of very interesting content that you will not find anywhere on the internet. So I'm sharing my with you will see my work today. I will show you my quantitative macroeconomic study. So as you can see from the screen, I gathered a bunch of macroeconomic time series which are related to the UK economy. For precision, it's 28 time series that I put together, and I performed a series of quantitative econometric studies and implemented a few models to have an idea more or less of the, let's say, the performances of the UK economy, but not so much about the performances, but the overall quality of the data. I performed some forecasts and I performed some VAR models just to have an idea about the interaction of multivariate models between macroeconomic variables. And from time to time, I tend to do these studies because all the data piles up, and then you have to update your system and so forth and so on. So, what do we do with the drunken sailor? So basically, I put together a few different measures of inflation, from CPIH, RPI, CPI. Then I have, you can all read the time series, which are unemployment and employment, then the value of retail sales and the chain volume of retail sales, which is seasonally, non-seasonally adjusted, then the gross domestic product, quarter-on-quarter growth, seasonally adjusted, chain volume measure. Then I throw in a few of balance of payment measure, which is in proportion of the current account, the total secondary income balance, and just the pure balance of payment percentage as a percentage of GDP. Then I added the gross value added measure just to have another idea of GDP. And then I throw in some monetary measures, which is the M4 growth, the M4 growth for a monetary and financial institution, then the Bank of England rate, and just one long-term average 10-year borrowing cost, more or less, just to have a broader idea of the whole thing, which of course it won't be enough because the economy, it's a very huge machine. So first things first, what do we find in when doing time series analysis? Basically we find that for example, the CPI annual rate, the inflation measures, or the RPI annual rate, the collection of data that we have month on month or quarter on quarter, it varies. We see that we have a trend which is not like a steady measure, but it's variable, it's volatile. So we need to analyze, first of all, if the time series is stationary. So we want to know if we have unit root. So we want to test for unit root. So we want to know if the time series is stationary or not, and if it's stationary, if it's trend stationary, or otherwise it needs first difference applying. Now I know these are it seems to be very technical thing. So for example, if we do the ADF test, the Dickens-Fuller test, we want to test for unit root, and we want to know if the data that we collect for inflation month on month or quarter on quarter or year on year, they are stationary or not. In a sense, if they are correlated with each other from period to period. The previous period tends to transmit volatility of inflation measures and volatility of prices to the following periods. Okay, so in this case we have a statistics of ADF statistic of 3, which is significant at 5% level. We don't have a unit root. The p-value is less than 5. So in a sense, the time series is stationary, but there is a trend. So in order to detrend to eliminate the volatility or the variance error from the normal inflation measure, we utilize a method which is first difference. So basically we subtract the data of inflation that we have this month, we subtract it from the previous month, so forth and so on. Let's say roughly works like that. It doesn't work really like that, but we have inflation of time t. Then we want to work out what is the difference of the data at time t and the data of time t minus 1, and then t minus 2. We regress the data, we do the subtraction, we have the difference. Okay, and so we try to eliminate what is the trend, and we see here first difference, and it seems that if we look carefully at the y-axis, we see that the range is between minus 0.02 and 0.03. So the range is narrower, and because we have inflation that goes from 0 to 10%, so it's a very wide range, so it means that it's very volatile. So another thing that we need to do is to have a look at this very nice ACF and PACF data. So when we have these bars with these dots on top which are outside the shaded area, we know that we have either autocorrelation and some seasonality in the inflation data that we collect for many years. Let's say in this case, I collected the quarter-on-quarter data of CPI inflation, of RPI inflation, of GDP, of money supply, quarter-on-quarter data from 1989 up to 2025, the first quarter of 2025. It's about 140 something data points. So what happens is that, for example, the inflation that showed up in the data that we hear on the telly in Q1, the first 3 months, it's somewhat related to what happened to prices in Q4 of 2024 in the UK economy. So what happened to prices during the Christmas season? It transmits its volatility to prices into the first 3 months of 2025. Now we are at the end of Q2 2025, like the end of June, so we will know that inflation at the end in the second quarter of 2025, for sure, as we look at these bars, it has a trend, at least for the 1, 2, 3, 4, the first 4 lags, more or less, 5 lags. So it means that for as far as back as 4 or 5 quarters before, volatility in the previous year, for example, it transmits volatility to the following period. And then here, it means that I have seasonality and I have a sort of moving average of inflation in the autocorrelation of data. And here I have a partial autocorrelation at lag 1 and 2. So maybe to have a clear stationary trend, I have to apply a first difference and maybe a second difference. I have to take the difference twice for the data in order that all the bars, they go into the shaded area. As in fact, you see the chart here, it says CPI annual rate difference. So when I take the first difference of the data, we see that the seasonality effects goes down to the second lag. The same, it's here, I have a very strong first lag autocorrelation, so it means that mostly the data are stationary, there is not so much volatility in the data, and I can work it through to do some forecasting, so forth and so on. So for all the 28 data points time series, I did all this work. I asked the machine to do all this work for me. And so we see that, for example, the RPI inflation measure, it's a very volatile measure, and when, for example, we apply first difference, we have a lot of problems for the ACF charts. One is that the ACF chart, the ACF result, the autocorrelation results, without the first difference, they are more, they exhibit less seasonality or less autocorrelation. So, for example, in this case, you would not You would be careful before applying first difference, because maybe the time series is already stationary. You can work with the data as they are. So you can see also from the original data here, you have a trend which is more or less contained between 0 and 2%, let's say. When you apply first difference, there is much more volatility. So for every and each time series, you need to work out exactly according to the data that you have, the statistical data that you have, the resulting p-value and statistics. Then you need to know exactly how to work with the time series that you are considering. So let's see. I have here, for example, the RPI of housing, which is an index that tracks only housing cost. The unit root test tells me that it's almost significant to 10%, but we will have some unit root, so we cannot reject the null hypothesis. And so we will need for sure to utilize a first difference to make sure that we don't have too much autocorrelation or partial autocorrelation. The KPSS, it's very difficult. The K is for Kwiatkowski. It's the cyclist, the Polish cyclist. Anyway, so we see here that the p-value, it's not significant at all at any statistical level. So we have unit root, we have non-stationarity, and so we have also a trend. So in theory, we will have to utilize a first difference method. We see that with the first difference method, the chart, it's a bit, it shows that there is a lot of volatility. So the data jumps from up and down with a wide range. So it's important to be very careful when working with the data, knowing, for example, when you're going to implement multivariate models, maybe you don't want to use the RPI housing time series when you are implementing a VAR or a multivariate model or a multivariate OLS regression, as we will see in a bit. Okay, so the same, we work through the CPIH, so the consumer price index, including housing cost, and we see that we have an ADF statistic value which is significant, at least at 10%. We have a p-value which is larger than 5, so we at 5% level, we will have to reject the null hypothesis. We have a unit root, so it means that the time series is not stationary, at least, and we have a trend also, and we can apply first difference, but we see here that the partial, the PACF and the ACF charts after the first difference method still exhibit these wide large bars with this dot outside the shaded area. So we have some lagged autocorrelation and partial autocorrelation, which basically explains that even if we try to enforce stationarity in the CPIH inflation measure, still it shows that it's volatile, and we have autocorrelation between lagged values. So that means that inflation in the previous periods, it tends to be an indicator of variance error and of trend volatility in the inflation measure. Okay, so going forward, we have RPI housing. We just saw that CPIH, excluding owners, occupiers, and the index is based at 2015 prices. So we see that we have an ADF T statistic which is 3, and in this case it's significant at 5% level because the data is 2.88. We have a 0.03 p-value which is smaller than 5, so we know that we can reject, in this case, the null hypothesis, and we can exclude that there is unit root. So the time series is stationary, but we have a trend. So we need to detrend. So you can see here, we have here a trend, a seasonality trend, and we have the first lag autocorrelation. So you apply first difference, and then you have the barrier that goes down. So you have AR1 or P1, or D1, and then you would apply a 1 or 2 MA2 moving average, and so you can make the CPIH measure 12 months percentage change, excluding owners occupiers, housing costs changed at 2015 prices, you will make it stationary and detrended, okay? By having one difference and two moving average, one AR model and two MA, one AR and two MA in an ARIMA model, then you will detrend and render stationary this inflation measure, which is the consumer price index, excluding owners, occupiers, housing costs, etc. And we see here the raw data, and we see here with the first difference we have a much more contained trend of data points, which tells us that the time series after the first difference, after the first AR term, it becomes more stationary and less volatile, less autocorrelated. Okay, so we work through all this data. We see when we have a lot of seasonality, which is typical of inflation measures. They have a lot of seasonality and autocorrelation, which is basically the expression of the volatility persistence in inflation. That means the persistence of volatility of prices. And yeah, that's interesting here. For example, people who are interested in the cost of the housing costs in the UK, I have here a preliminary just analysis of the time series, the RPI, retail price index of rents. So that's an inflation index that tracks rents prices. And I can tell you that the data is not stationary, so there is a lot of autocorrelation. Now, in statistical terms, autocorrelation translated in the real world, it means that the inflation crisis of rent prices, it's correlated to past times that rent has been increased by landlords. So if the past year you have volatility of rents, I mean rent prices going up, okay, you have a cost of affordability in the rental sector, you can be sure also from the data that what happened in 2024 or in 2023 or in the previous 5 or 10 years, because the autocorrelation, it spans along the time series. It will fit through in volatility of rent prices also in the present time and in the future. So you have a lagged effect that fits through, it has a pass-through effect of inflation. That's why it's very important to measure these things in a empirical manner and say, okay, the ADF test, the Deacon-Fuller test tells me, okay, I have a minus 2.38 parameter here. This is not significant at all at 5% level, because the value, it has to be larger than or smaller than smaller than minus 0.288. Here I have minus 2.38, which is larger. So that means that the inflation measure that tracks rent prices, the retail price index that tracks rents across the UK, it's non-stationary. That means that if you look at this graph here, you see there is a very gentle downward slope. And 1, 2, 3, 4, 5, 6. You have at least 8 lag period, which explain a seasonality of 8 lags. It means that for as long as 8 periods before, there is a pass-through effect of rent, of volatility, or just the past rent data. They do have a lagged effect on the present data and on future data. So you have what technically is called a pass-through effect of inflation, that it's autocorrelated from the previous rent increases of landlords applied by landlords. And so you have a trend. You have a moving average, you have a trend in which is autocorrelated, and you have here, yes, the first and 2 lag period of autocorrelation. So you have a moving average which spans back as far as 8 lag period, and you have two lags of autocorrelation. Now, when we do d equal 1, we apply the first difference of data. That means that I take the data from 2025 and I subtract from the previous data, let's say. Then you see the charts below, RPI of rent, difference. So apply first difference. You see that all this mumbo jumbo of this sloping thing of bars and dots disappears. And so it means that the data has become stationary, and I don't have autocorrelation with the previous periods. That does mean that the landlord won't increase rents if you apply first difference, but it means that you need first difference to work the data. And for example, if I want to interpolate the rent inflation measure with, I don't know, wages, I need to apply first difference to have a stationary set of data that will allow me to have an output which is not volatile, and it does not have a pass-through effect of variance error or lagged volatility, let's say, okay? So I don't have messy results. I hope not to have. Let's see, you see here how this other CPI index, it's very volatile. It shows a lot of autocorrelation. So here we have a CPI, here I have a CPI index which is very much utilized, for example, in Euro area analysis of data, because it's excluding energy, food, alcohol, and tobacco. This particular inflation measure, it's utilized to to do some financial engineering and build the inflation linked swap. So you do a bootstrapping of this inflation measure and you interpolate with a zero coupon and you build the inflation swap curve, okay? But you need, basically, when these geniuses do this stuff, they use this measure because it's an inflation measure which excludes all the volatility. It excludes energy, it excludes food, and it excludes alcohol and tobacco, okay? So just I gave you a hint about something. And we have here, it's statistically significant almost at 1%, so we don't have unit root. We can reject the null hypothesis. The time series is stationary without first difference, but we have to apply first difference to detrend this specific CPI measure. Now let's see. I want to show you that inflation is very volatile. It's a set of data. Any kind of inflation index that you just see on the telly, oh, inflation, it's up 3%, it's down 2%. You see the numbers vary very much month on month and year and quarter on quarter, because price is very daily. Especially with the digital economy, we have very much more volatile prices. And for example, if we consider another set of data which is related to employment or unemployment, we see that unemployment has a lot of moving average seasonality. It has some autoregressive lagged autocorrelation, partial autocorrelation. So you can apply a first difference, and then the data becomes more or less stationary, although we have some exhibit of still some second and third lag moving average seasonality and some partial autocorrelation. So probably when you are implementing an ARIMA model, you will not do AR1, MA1. Maybe you will try to force the ARIMA model and do AR2 and MA2 and apply a D1, a first difference. So maybe you will squiggle out all the autocorrelation and partial autocorrelation of the unemployment, basically seasonality in the trend of unemployment. Now we see that the data here, we see that the trend has turned and it's steadily going up a little bit around 4.4, because it was 4.4, then it was 4.5, then it has become 4.6%, the unemployment rate. So that's one thing. Then I analyze also the employment rate, because I want to know what are the level of employment, okay? So we are always around 70 million people or something like that. Not 70 million people, it's impossible, sorry. The index value is around 70. And the employment rate time series, in this case, it captures the quarter-on-quarter percentage change of employment. So I took the index and I basically calculated the quarter-on-quarter percentage change, and then I stuffed it in the whole Excel spreadsheet, right? And then I'm able to see the quarter-on-quarter percentage change in the employment level, age bracket, its age range between 16 to 64, sorry. So I know that the time series does not have any unit root, it's stationary, right? But there is a trend. Okay, so we need to detrend, apply first difference. You see here there is very few dots outside the blue shaded area. When we apply first difference, the time series is almost completely stationary. So this is very squiggled only inside the shaded area, the blue shaded area. So we don't have volatility, we don't have lagged correlation or partial autocorrelation, whether it's the moving average of or the trend of the data or the autocorrelation of the lagged values. Okay, so I hope you are understanding something. So we see here that for example, the employment and unemployment data, they follow pretty much a trend. So if unemployment starts to go down, we can presume that for quite some time in the following periods, unemployment will go down. So more people will be in work. When we see a change of trend, as we have seen now, unemployment going up, so going from 4.2 to 4.3, quarter after quarter, to 4.4, 4.5, 4.6, we have a trend, and I can see that in the data, yeah, because we have this slope, and we have autocorrelation between periods, and I know that it follows a trend. So when unemployment starts to go up, tick by tick, it goes to 4.6, maybe goes back to 4.5, then going back to 4.6, but it goes up to 4.7, etc, etc, etc. So it stays on trend for quite some time. So difference is unemployment as a trend, inflation is very volatile. Okay, this reflects exactly what happens in real terms. Okay, now we have the value of retail sales at current prices seasonally adjusted. And for example, I know that there is unit root, so the time series is non-stationary, and I have to apply first difference. Okay, so although first difference is significant at 10%, but when I apply first difference, I mean the raw data is not so bad, really much volatile. When I apply first difference, still I have some out of whack dots and bars and dots. So I know that retail sales, it has some cyclicality or seasonality. Like people, they tend to spend a lot, for example, during this time, like in summer season, because the weather is good, people go into the shop, they have bargains and discounts for the summer sales, or everything must go, or something like that. Or there is a lot of shopping during the Christmas season, while for example there is less shopping in the first 3 months of the year, between January, February and March, because you spend all the money in December. So there is seasonality in the retail sales data, whether it's the value of the retail sales or is the volume of the retail sales, which is the quantity of sales that there are in aggregate into the economy. And so I know that retail sales, they have some sort of cyclicality. Okay, now let's have a look at GDP, quarter on quarter growth, chain value measure, CVM, seasonally adjusted, and in percentage terms. Now here we have a minus 11, so this is a very big statistical point, and for sure we can exclude that there is unit root, so the data is stationary in itself. So GDP data quarter on quarter, this time series specifically, it's stationary, it's not very much volatile. So GDP quarter on quarter is not very much volatile. Maybe month on month you can have more volatility, but because it's a question of basically a mathematical question, because you increment the frequency of data. Instead of having 4 data points per year, which is quarter on quarter, you have 12 data points, which is month on month. So you have more variance and you have more volatility, right? Although the variance, even if it's month on month, is not very huge. I mean the standard deviation. So GDP, it's not by definition very volatile. Okay, it cannot be very volatile, because GDP is the aggregate of goods and services which are produced into the economy, or you can measure it in some other ways, like adding the balance of payment, or you can measure the aggregate output. So all the stuff that has been produced in the economy, there are different nuances, and I'm not an expert at all, but you can see here that it's a flat line, and then you have this big down up, which is COVID. So you have a big down minus 10% and up 20%. So that's the COVID volatility. But GDP, it's not volatile. It's stationary in itself. You don't need to apply any first difference. When you apply first difference, maybe you mess up the data. So you can work with the raw data as they are. And so we know that GDP is not very much volatile. We know that, for example, here, as I was saying, retail sales, they have cyclicality. And consumers know that there is cyclicality. You go to shop when there are discounts and bargains, so you do more shopping during summer or during Christmas season. So we see here the chain volume, so we measure the volume, so the quantity, not the monetary value, the quantity of stuff that is sold and bought by the consumers in the economy. That's not seasonally adjusted. And we have unit root, so the data is non-stationary. You have to apply first difference because there is cyclicality and volatility in data. And applying first difference, it normalizes a little bit. There is less autocorrelation and partial autocorrelation, and so forth and so on. Now, let's see the balance of payment. It's stationary, and you don't need to apply first difference. So it's a lot of work just only to have a precise idea of the data, and then I could work through again and ask for the kernel density curve. That it's, you can see this the line that fits the bell that fits the histogram distribution of data, that the kernel density, that the kernel then you test for the unit root, and then you have this fancy plot, which is these blue dots. All the blue dots which are on the diagonal red line, that's fine. But when you see the blue dots which are outside, that means that you have that's wrong. You have outliers, you have fat tails data, which is here. You see here 7.5, you have this blue square here and here, which are very far in the distribution. So at some point in time, the CPI index measure, it has registered in the data plus 7.5 inflation or plus 5% inflation, which has been recorded quarter on quarter. So you have this out of, not out of sample, which is another thing. You have a fat tails, far in the tail, very extreme outliers data, which are not, for example, 0.5 or 1% inflation, normal measures that we hear every time. But for example, after COVID, we had 5% inflation, 10% inflation, 12%. So those are outliers, are some stuff that we never saw in our lives. They, what the heck is going on? You can see in the chart that there are, with these dots, which deviates a lot from the range, and you have the distribution which is far in the tails. Then you see that there are extreme outliers in the distribution of data. So that means that it's very likely that you have a very high kurtosis, and so the distribution is leptokurtotic. Sorry if I said it wrong. And you have a very volatile data, although it's these are macroeconomic variables, or inflation, or retail sales, or money supply, or interest rates, so forth and so on. Then I decided to test the distribution of data, and I asked the machine, please let me know what, I don't know if I have to, let's try to, okay. I asked the machine, please let me know exactly the data, what is the best fit distribution. Why it's important? Because we start from the assumption, like those that work in this technical field, sometimes we start from the wrong assumption that the data is normally distributed, but instead it's not normally distributed. For example, the RPI, Retail Price Index, this is very important also for you watchers and listeners. Just thumbs up, give me a like. You can see here best fit log normal. So it means that you have a normal distribution which is on a logarithmic scale. Okay, and that's what fits best the data that are collected for the RPI index, the retail price index. So the log normal distribution, it has a very peculiar characteristic, which is a multiplicative effect of the distribution. So it means that inflation data, they have a pass-through effect and they have a multiplicative effect. Like if I have a 1% inflation, I have a multiplier effect. So the following period I will not have 1%, but I will have 1% multiplied by some factor, so I'll have a 1.5% inflation. So it means that RPI, it's very volatile, but the distribution of data is a log normal distribution, so it has a multiplicative effect, which is somewhat, I won't say very dangerous, but if inflation multiplies and increases by multiples, then probably it's a bit of a problem. You tend to have a very high inflation, which is not the best thing when you aim at price stability. And in the case of the UK economy, the 2% inflation target is established by the Exchequer of the Treasury Department, and it's basically imposed to the Bank of England. Okay, I can assure you that the starting assumption of having a 2% target of inflation imposed by the Treasury is wrong, and the Bank of England is forced to work with a wrong assumption. Now, when you go to school and you do a very simple math problem, let's calculate the perimeter and the area of this triangle when I know the base and the heights of this triangle. Okay, so you do an hypothesis and you say, if I know the base and the height of the triangle, I do the multiplication and I know the area of the triangle. Okay, now it's the same for the Exchequer. When you start with the wrong assumption and you say you must hit the 2% target, but I know that the distribution of data of inflation is not symmetric to 2%, but for example RPI, the retail price index, it has a log normal distribution which has basically the inflation data, it works by multiples. Yeah, the log normal distribution, it has a multiplicative effect of the distribution. So how on earth those that work with monetary policy can adjust monetary policy to achieve the 2% target? You start basically with the wrong assumption. It's wrong tools, it's wrong, it's a bug job in basically in monetary policy engineering of achieving 2% target. Because in my humble opinion, the 2% target imposed by the Exchequer, but not by the Exchequer, at large in all developed economy, and this was the glorious idea taken from the Central Bank of New Zealand, it's a wrong assumption from in economical terms, in econometric terms, in statistical terms, because inflation is not steady, it doesn't sit at 2%, it goes up and down, it's volatile, so you cannot pretend to hit 2% and it stays there. Now we have original RPI percentage change over 2 months. You see, you have a bell curve, you have a distribution, that's a normal distribution, but you see the data goes from 0 to 20 or 40, so you have a huge range of values, and you will never ever hit the 2% and inflation will sit there, because it's contrary to free market and the supply and demand equilibrium of prices. You know, if there is more demand for something, then prices go up and we deviate from 2%. So how on earth the central bank is supposed to work with the wrong assumption that price stability is 2% and that's it? It's wrong. So I invite you to watch my video about monetary policy revolution. So you need to basically utilize the central limit theorem, take the inflation data, standardize it, symmetric at 2%, you see what is the volatility range, you utilize a Garch model to see the conditional volatility, you do a much more sophisticated Taylor rule formula, and then you can try to work out more or less and see in which basically business cycle you are. Inflation is going up, for what reason? We have stagnation or the economy is expanding, so forth and so on. But you cannot work from the assumption that comes from the exchequer and say, no, it's 2%, cut interest rate. It doesn't work like that, because inflation will not stay at 2%. And basically, it's a dog that wags its tail, and it's the merry-go-round that goes around and around and around and around, and we will never achieve 2%. I showed in my other video that the average for the past 40 years, the average inflation in the UK has been 3.3%. So the Bank of England has never achieved for the past 40 years 2% target. So we are imposing a target, not we, I mean the Treasury pretends to impose a target which is totally bonkers. Okay, so when you deal with data, with something that is based on facts and formulas, and the empirical working of things, like is math or physics, you must start from the right assumption. You must have the proper hypothesis to arrive to the result which is effective. Otherwise, and we know that inflation is very high, we have a cost of living because the wrong assumption have been placed at the heart of inflation targeting and monetary policy. So the whole construct, in my humble opinion, it doesn't work properly. It needs to be worked in another way, as I explained, etc., etc., etc. But I'm the last man on earth. So let's talk about multivariate OLS regression. So ordinary least square regression. So we want to run a multivariate. It means that I have 28 variables, which are the 28 time series. I have inflation, unemployment, employment, GDP, and then I have the balance of payment, and the gross value added, and then I have interest rate, I have money supply. All these variables are interpolated between each other, and the linear regression, I want to achieve the smallest error, so I select the data points which have the squared error, which is the smallest, which is the nearest to the line that basically fits best the scatter plot, the linear regression. Okay, and why it's useful? Because I have a dependent variable, CPIH inflation, and I have 27 independent variables. So what it means that I have 27 independent random variables, and I want to know the expectation of inflation. What happens to the expectation of inflation? So we go and check the p-value. We have a p-value 0, so it's statistically significant. The t-statistic, it's good. We have a small standard error. And so what it means? It means, for example, that strangely enough, if retail price index, it moves, no, that's the constant, so I'm looking at the wrong thing. Let's take this here. Alright, so CPIH, okay, excluding owners occupiers measures, prices are chained to the 2015. Okay, so what happens? The multivariate OLS regression, remember the dependent variable is CPI, inflation annual rate. So if the CPIH measure moves by 1 unit, goes up by 1 unit, then the CPIH measure increases, it varies by this coefficient, 0.0034, which means that for every 1%, which means more or less, for every 1% increase in CPIH, I will have a 0.34% increase quarter on quarter of CPI on an annual basis, okay? Year to year. So that's why we have these random variables, which are all the random parts in the economy which are moving around, and there is this poor inflation measure, and say, oh well, these things, all these random variables, what will be the linear correlation with inflation, with the inflation. Okay, so that's both for both this CPIH measure. Here we have housing costs and excluding housing costs and council tax. So for every 1% increase in this measure, excluding council tax, we have a 0.67% increase bump up in the broader CPI measure. Now, the same is for RPI, so we can see from the multivariate OLS regression that different kinds of inflation index which track prices in the UK economy, they are correlated. They are linearly correlated. What is linearly means that is a linear equation of the type epsilon equals ax plus b plus some epsilon, which is an error terms. Okay, so I have the intercept coefficients and the slope coefficient of a line that fits a series of data, and then I want to estimate the ordinary least square error. So I want to estimate those data points which have the squared error, which is the smallest. So it means that they sit exactly on the line. Now, I think that there must be the chart. Yeah, here we are. Okay, so that's a quantile, but the idea is that I have a lot of dots. These dots are the interpolation between CPI, this one, inflation, and all these other random little scribbles, cringes things which are in the economy. CPIH, housing costs, excluding council tax, RPI, unemployment, employment, GDP, the balance of payment, the retail sales, the money supply. So this is a measure, is a technique which is helpful to make me understand if GDP goes up or down, what is the linear relation between GDP and inflation, okay? Or if employment or unemployment goes up or down, what is the linear relation with inflation? And we know Phillips curve, but I can estimate here, for example, if I have a value which is statistically consistent. Okay, here. Let's take this one. Okay, very classic Phillips curve, which I like a lot. We have a p-value which is statistically consistent. T-statistic is good. The standard error is 5 points e to the minus 0.5, so it's 5 points after the 0. And we have a very small coefficient. But nevertheless, this tells me, for example, that if unemployment goes up by 1%, strange enough, inflation goes up slightly, but ever most slightly, which is very counterintuitive, because if unemployment goes up, inflation goes down. If unemployment goes down, inflation goes up. That's the Phillips curve. All right. But nevertheless, I can estimate the linear regression, and all these strings of data, they are like dots, and then I want to estimate the OLS, the ordinary least square error. Okay, and then what is the dot that sits the nearest, which has the squared error, which is the nearest this line, linear regression, which is not exactly this one, but for example's sake, we say that, then that's what is statistically significant. Okay, so after a long blabbering, we have here CPIH. This is a very nice model because I can estimate what is the residual. Okay, because I can apply first difference, then I have residual error, variance error, or residual volatility error in data, and then I can estimate what is the range of volatility error, the residuals, so I know exactly, and then I have an ACF, which is very squashed, and then I don't have any autocorrelation, okay, so I have squashed the CPIH, and in the end I have here a very nice table. It tells me, okay, the significant predictors with a p-value which is smaller than 0.05, so smaller than 5%, are the CPIH measures, the RPI, and unemployment, what I showed you just now. And for as long as these independent variables, these significant predictors, they move by 1%, they will have an inference coefficient on the dependent variable, which is CPI, okay? And then here I have variance inflation factor multicollinearity. What it means that, of course, if I measure CPI and I measure CPIH and RPI, these are redundant. They are very similar measures of inflation. So it happens that the system tells me, oh, just bear in mind that you have multicollinearity, like multiple time series that they are strictly linearly correlated, okay? And so we run through all the OLS data, all the OLS models for the inflation data, RPI, the significant predictor of RPI is the balance of payment quarter-on-quarter change, net investment position, I believe. So that's important to know that, for example, the RPI, a predictor of RPI inflation, it's something which is very unknown, and it's completely in another part of the economy, which is the balance of payment. The balance of payment basically tracks imports and exports, okay? In the percentage change in this case based on the net position of inflows and outflows, okay? So what it means that it's very important. RPI, retail price index, they are very sensitive to the balance of payment. So it means that the UK economy, of course, it's very sensitive or sensible to price shocks which happen through the transmission mechanism of the balance of payments or through imports. Okay, so imports and exports, they tend to be a predictor of the RPI. And of course, I have forgotten to include the PPI index, but I cannot include everything in all things. Now let me pick something which is not inflation, because we are talking about inflation like the world's end in Camden, and I hope you are all having a nice chill beer with this very hot weather. Hot. Now here we have residuals, RPI, percentage change over 12 months of rents. So the retail price index, which tracks rent prices across the UK, you can see here, like in these periods, this huge bar going in 2024, we have a huge residual error variance. So this actually tells me that there is a lot of volatility and a lot of autocorrelation for what concerns rent prices and rent inflation, and the index that tracks the inflation of rents across the UK. Okay, let's see what the OLS multilinear regression tells us. Okay, now our dependent variable now, it's RPI of rent 12 months percentage change. Okay, the independent variables are all the other variables. Now let's see what is statistically significant, and we have RPI. Okay, so this is very interesting. Okay, so here it tells me, strange enough, that if RPI, the inflation measure of retail prices, which is chained to the base year 1987, goes up by 1%, I have a negative coefficient of 0.49. Okay, so I have a negative linear regression correlation between RPI, the general measure of retail prices, and the inflation index that tracks rent prices. In reverse, the RPI that tracks personal expenditure, so the inflation measure that tracks the personal expenditures of UK consumers, it has a positive coefficient of 0.45. So it means that you have consumers which are spending 1% more quarter on quarter than the RPI that tracks rent prices will reflexively go up by 0.45%. Okay, so from this result we can infer that when we have an increase in the measure of inflation that tracks the personal expenditure of UK consumers, we can presume that 0.45% of personal expenditure, it's gone towards rent inflation. So it means that 0.45% of the RPI inflation cost or personal expenditure, it goes towards RPI rent. Let's say like that. For 1% increase in 1% bump up of personal expenditure, I will have a 0.45% bump up of RPI rent inflation. So the rent component, it's a big part of personal expenditure for the ordinary consumer. Now, rents, they are negatively correlated to the value of seasonally adjusted retail sales. So it means that if consumers are spending 1% more in value of retail sales in aggregate, I will have a negative coefficient of minus 0.4. So it means that if I have more disposable income for retail sales, I will have a dampening effect on rent inflation, okay? Which seems to me not obvious, but logical, okay? If the consumer is spending on sales, on shopping, I will have less inflation on rents, or less spending on rents, because the consumer is spending on shopping, on retail sales, okay? Okay, the same is for the chain volume. So if I have higher volume, I have a positive coefficient. So I have a positive linear relationship between the volume of retail sales and RPI rent inflation. So I have a negative coefficient for the balance of payment in percentage of the current account. Okay, so if the balance of payment goes up, then I have a negative effect of minus 0.19 on RPI index that tracks rent prices, and so forth and so on. I have here a positive coefficient on bank rate, and it's at 0.72. So it means that if the cost of borrowing, if the Bank of England hikes interest rate, I will have higher rent inflation. Why? Because the landlord will see the mortgage costs going up because of higher interest rate from the Bank of England, and this has a pass-through, linear pass-through effect on RPI that tracks rent prices index. So I have a positive coefficient of 0.72, which is almost 1 to 1, 1%, 1 unit, okay? But nevertheless, the residual of error variance, they are large. There is still some autocorrelation. We have the nice thing here of the significant predictors. We have gone through all the significant predictors. Now RPI rent, CPI index. Let's see what basically. Okay, let's see. Unemployment is correlated to inflation. Okay, so if inflation goes up, unemployment goes up. That's I don't know. I will have to think about that, but nevertheless, because the coefficient is 522, so I don't know if the model, the linear regression, is run through properly. It's difficult now. Okay, here it's more reflective of the Phillips curve, in the sense that if the CPIH inflation, excluding owners occupiers housing costs, goes up by 1 unit, it means that unemployment decreases by minus 5.3. So unemployment goes down, CPIH goes up. It's perfectly logical in economic terms. And the significant predictors are retail sales, the balance of payment, and the bank rate for unemployment. Let's go and double check. Yeah, okay, yes, okay. So we see here, for example, that the cost of borrowing is a predictor of the level of unemployment in the economy. So the long-term cost of borrowing, if it goes up by 1 unit, we have a positive effect on unemployment, so also unemployment goes up. But instead, if we have the Bank of England hiking interest rates, okay, so we can explain this very clearly. In which terms? So the Bank of England hikes interest rate. In the short term, I have a negative effect. So unemployment goes down, no problem, there is no unemployment. But in the longer term, if the interest rate, they are higher, then I have a slowing effect, and then I have rising unemployment. So the moment the Bank of England hikes interest rate, the labor market is steady, and unemployment can keep going down, so people find jobs. But in the longer term, if I have higher interest rate because inflation is high, then unemployment starts to go up. This is exactly what has been evolving in the UK economy. The Bank of England has kept interest rate at 5%, unemployment was steady at 4.2%, 4%. Then because interest rate have become higher for longer, then now unemployment has changed the direction of trend, is going up here. So that's the basic logic of things. And if I have an increase in the balance of payment, then I have an increase of 0.14 units on unemployment. So the only thing which is not clear to me is that if I have a larger deficit, I will have higher unemployment, or if I have a narrow deficit, I will have higher unemployment. I don't know. I presume that if I have a larger balance of payment deficit in proportion of the current account GDP, then it's conducive of higher unemployment, because less people are in work producing more stuff within the economy, so you have to import more inputs from outside. That means the less input are produced within the economic engine of the British Isles. So a larger balance of payment deficits probably also procures a bit of higher unemployment. Now, I want to see the money supply. Let's talk about money. Money. Do you smell it? Do you smell it? I smell money. Just 1 second, because I'm sure these are at the bottom of the thing here. I smell money, right? And then we will go to the ARIMA model, and we'll have to call it a day because it's already 1 hour that I'm blabbering, and it's a very long content. Please just leave a like, subscribe, because you will not find very easily this kind of I know it's a bit messy because I had to show you some annoying or boring stuff. Okay, now we have the quarterly 3-month growth rate annualized of M4, so money supply, the broader monetary base M4 money supply, based on monetary financial institution, sterling, liabilities to private sector, seasonally adjusted. Okay, so what are the independent variables that generate some linear relation with money supply? Let's see if we have something here. Okay, so inflation is a monetary phenomena, and so we see here we have two contrarians, in the sense that CPI inflation, one measure it's negative coefficient, the other measure excluding council tax, it has a positive coefficient. Let's assume that if we have higher inflation, of course we have higher money supply, because inflation, it's definitely a monetary phenomena. Here I don't have a good p-value. What is here? No, it's here. It's these two. Sorry. These two here. Sorry about that. It's this one. CPIH, which are the same. So we can assume that this CPIH index, which is not on a 12 months horizon, has a positive linear correlation with the M4 money supply. Okay, this one, right? You can see here. For 1 unit inflation CPIH going up, we have a 0.57 coefficient of growth rate in M4 money supply. So here we have, okay, so if we have CPI index excluding energy, like core inflation going up, it has a negative coefficient of M4 minus supply, so that's an inverse correlation to minus supply. Here, okay, if we have 1 unit increase in volume, the quantity of retail sales, it means that there is more money supply, so there is more people, more disposable income. Yeah, money supply is correlated to, it has a linear correlation with the other measures of money supply. Here we have the quarterly amount outstanding of credit in the economy. So of course, we have a negative coefficient, which is very interesting by any means. Okay, so money supply in general terms, in gross terms, the significant predictor of M4 money supply growth are inflation, retail sales, the balance of payments, so import-exports as a percentage of GDP, and also the other measures of money supply, which seems to me it makes complete economic sense. If there is more money supply, we have higher inflation, we have more retail sales, we have a larger deficit because we have more imports than exports, and if we have an expansion in credit, so in outstanding lending to consumers, we have an expansion in M4 money supply. So it makes complete economic sense. And then you can appreciate that the multilinear OLS regression, it's a very useful model, although it's a linear regression. It doesn't have any fancy stuff of quadratic equations and stuff like that. Now, we can move forward to the forecast. Okay, so here we are. Okay, so here we have an ARIMA, and we don't have any seasonality effect. Okay, so we don't have a SARIMAX model, we have only an ARIMA model. Okay, so the ARIMA is the autoregressive integrated moving average. I was telling you before, the time series, the data are non-stationary, they are correlated. We have autocorrelation function, partial autocorrelation function. So the ARIMA model, it integrates ARIMA, AR, so it's an autoregressive integrated moving average. So what we do, we have an AR parameter, PQ and D parameter, PDQ parameter. So we apply the first difference, we apply a P parameter, we apply an autoregressive and a moving average parameter, and here we see best model ARIMA, it's 0, 1, 3. So it means that to have an accurate forecast, we have 0 with the P parameter, we apply 1 first difference, and we apply 3 moving average to have a stationary set of data, which basically exhibit the smallest possible error variance, and then machine gives out a forecast, and it tells me, okay, for the next 4 quarters, CPI inflation will be 0.3, 0.4, 0.4. Okay, and we have the residual distribution. That's the same. The QQ plot, okay, it's to see if there are these dots which are outliers, like this dot here, it's here. Okay, we have a large outlier, extreme value, which is a tail value of the residual distribution. Okay, and we have a kurtosis of 18. When the kurtosis is larger than 3, we know that the distribution has fat tail values, some values which are very large and are out of the ordinary mean value of the distribution. The forecast it's for a 0.3, 0.4% quarter-on-quarter inflation, and it's not seasonal. Now we have RPI. RPI, you see that it's not very well. We call this out of sample forecast, out of sample data points. The out of sample data points, they are not very well exactly concatenated. So as a graphical difference from this, you see these are pretty much well concatenated. The out of samples, it follows the trend more or less. Here we have a zigzag, which is not very nice. It's not in line with the data. So the auto sample, you have to take it with a pinch of salt. You have to believe it or not, because it's 1.42, then 0.72, so there is a lot of volatility and it's not very accurate. Okay, but nevertheless, you have some sort of forecast. The same is for RPI housing. So I was showing you before, for example, we can see it now. When we have the ACF residual, which has these dots which are outside the shaded area, then it becomes evident in the forecast, because the forecast, the auto sample forecast, is not precisely concatenated with the data, so you have a forecast which is not very reliable. Okay, so all my explanation at the beginning of the video, it's useful to understand why you need to have stationary data, because then when I work through the auto sample forecast, I have this zigzag, and basically it's waste work. Okay, so it's a wasted effort. So it depends. Even if you utilize a auto-optimizing ARIMA model, is not always optimal. Okay, but nevertheless, for all the RPI housing index, so forth and so on, all the forecasts, they are for volatile inflation, but we have 1.2, 1.7, 0.5. The forecast is for positive inflation and maybe higher inflation, which deviates from the 2% target. But of course, take it with a pinch of salt, because here we have a very precise forecast. Okay, instead of having the zigzag, we have CPIH, excluding non-occupiers, and we see that the auto sample forecast shows me a uptrend in inflation, 3.4, 3.8%. So the machine is forecasting an auto sample 4-quarter horizon forecast into 2026 of inflation going up. Now, I don't have a crystal ball, but I can take the data point as an informative data point for inflation. And then, I don't know, if I'm deciding monetary policy or fiscal policy or anything related with inflation, then I have an auto sample forecast. I don't give a damn, but maybe I should be careful that if I have higher inflation in the following periods, then my borrowing costs will be higher, and then it's a bit of a problem for fiscal policy or for the Bank of England if they have to do quantitative tightening, so forth and so on. Now, another CPI measure, auto sample, you have a huge auto sample 1% jump in inflation, 3.4 up to 4.8. So, I don't know for which specific reason the UK CPIH measure will go up to 4.8%. I hope the machine is wrong, but I will keep this data for me to see how the real data in the economy will evolve. And then I will match it with my forecast and see, okay, I did a good job, I did a bug job, I need to work better the code and something like that. This is mostly for my own academic research, stuff like that. Now, here the RPI also tells me there is a pattern of consistency that inflation will tend to go up towards 4% again. There will be a huge moment for fiscal policy and for monetary policy, okay? Here we have RPI, that's the auto sample, that's not very concatenated, so I will not, it would be very painful to see inflation at 5%. Now, RPI inflation rent, it's actually standing now at 8%. And if I want to, I will recall you the data now. Rent inflation here, the last data was 6.1%. But if we take, here is specific, the rent index that measures the 12-month percentage change, you can read it by yourself, it's actually at 8%. And the auto sample, it's pretty much very concatenated, and so it tracks me 4 quarters forward and 8.3, 8.4 inflation for the RPI that tracks rent prices, which is very high. If inflation has to be 2% target, tell me how do you square out an 8% RPI rent? Okay, so that's why it's very much evident to the ordinary plumber, the carpenter, the people who go to the Tesco shopping and say what the bonkers breeders is going on, what the bonkers is going on in Britain with prices when rent it's 8% and we have rent unions and stuff like that. So by no means at all yeah, the 2% inflation target, it's something achievable. So I don't want to repeat myself, but we see here that's completely bonkers and we discard that stuff, of course. Now CPI index, energy, food, tobacco, okay, it tells me, okay, go. Now, inflation will be 1.3%. This is very, very strange. I don't know from where it comes out. It's not very much concatenated. I will basically be very, very vigilant from this data. Now, unemployment. We saw in the first instance here, okay, we take the data from unemployment and I said, you see here there are these bars and these dots and they have a slope. That means that unemployment is a trend, is a moving average, and there's two lag of partial autocorrelation function, right? So what I said is that if unemployment starts to go down, you have a trend of a long time, even years, when unemployment goes down. Now the trend has changed and the trend is your friend. Not in this case because it's not very nice, but we have a trending unemployment of going up. So we have unemployment growth. We don't have GDP growth. We have unemployment growth because you have to be better off. You have to be better off work. Okay, you have to be a benefit. That's how it works. You have to be dependent on the state because they need voters. They pay the benefit, you vote for them. That's how it works. It's pitiful. Anyway, I see the trend here, in the middle, autocorrelation function. You see here. Now, this is concatenated because it gives me out. So I have two autocorrelation terms, one first difference. So what happens? I have an auto sample which is very much concatenated and in trend. It tells me, okay, unemployment will go 4.6%, but it's already at 4.6%. So it's very redundant. And yeah, so I can assume that these numbers here are wrong because the line coincides with 4.5, 4.6. So the auto samples tracks, it should be 4.7, 4.8%, okay? But pretty much it's concatenated with the upward trend in unemployment. So we can expect higher unemployment. And if higher inflation materializes, it means that UK confirms to be in a stagflationary quagmire, which is, I'm repeating over and over again, UK has entered stagflation in Q4 2021, and the Q1 2022 was the disaster of stagflation. Okay? Now, the employment rate pretty much will be stable. Auto sample, not so great. Now, value of retail sales. It tracks more or less similar value. 4 quarters, 2.5 to 3%. So growing value of retail sales. We can be sure that if prices go up, of course, the value of the stuff that you ordinary consumers buys goes up. So the value of retail sales goes up because the prices, inflation goes up. What counts is the volume because you can buy less stuff and pay a higher price. Okay, the consumer knows pretty much. Okay, so for what concerns GDP growth, it tells me, okay, the auto samples tells me, okay, GDP growth will be steady at 0.4%, quarter on quarter. Not good, not bad. We will have to see how will be GDP growth in real terms. Now, here, okay, it tells me, okay, but if the value of retail sales will go up, the concatenation of auto sample is not very good. But it tells me, okay, probably you will have less stuff. So the volume of sales, it could be that it will be lower, but the price will be higher. So you will have, in aggregate, lower quantity, less quantity, higher prices. But, you know, always my task, of course, is to double check with the real data and see how I do the work of modeling, quantitative modeling. Okay, I hope you are enjoying the video and just thumbs up, subscribe. You will not find this kind of material anywhere. Now, here we have the balance of payment is structurally negative because we have negative percentages of balance of payment. We have a structural deficit, which is not fiscal deficit, it's balance of payment deficit. So these data, they are very difficult to work out also for the machine. And yeah, but yes, but no, but I cannot comment in realistic terms on the forecast, but we see that all the data, they basically the machine works through negative balance of payment, so a structural balance of payment deficit. Like for example, in the data forecast we have minus 1.1%, minus 1.5%. These data, they cannot be taken as a forecast because the balance of payment is very volatile. It depends from the business cycle, so I cannot make a data point estimate of the balance of payment. But I can make a data point estimate of the gross value added in the economy, which is another measure of GDP. You can measure the amount of goods and services which have been sold or produced in the economy, and you can measure the growth or the decrease of goods and services. Or otherwise I can measure the gross value added in the economy. Okay, so the GVA average out of sample forecast, it tells me, okay, we will have a gross value added as a measure of GDP quarter on quarter, more or less 1%, which is more or less in line with the past quarters. So we have an out of sample which is not much volatile. We can double check if we have 1% gross value added quarter on quarter. If deviates, then it means that the economy is performing better or worse than my forecast. Okay, all the other ARIMA models are very difficult. What we can consider here is probably that we will have more credit creation, probably some sort, but you can see the shaded area, it's huge, so there is a lot of uncertainty in the model output. Now we can see that the out of sample Bank of England interest rate benchmark, it tells me that interest rate will slowly go towards 4%, so we can expect one rate cut in the coming quarters. That depends on the macroeconomic condition, where is inflation, where is GDP, where is unemployment, where is servicing inflation, so forth and so on. And we can expect that the long-term average 10-year cost of borrowing will be around 4.6%. Okay, so in broad measures, I can produce some reliable forecast, and I repeated the forecast with the seasonal ARIMA, but more or less results are pretty much the same. And I will have to stop the video here because it's a lot of things to digest, because we could go on for another hour, to say the least, because I can show you the VAR models. So what are the autoregressive matrices correlation and the impulse response between macroeconomic variables. So if I have an impulse from the balance of payment, what will be the impulse response from RPI, from the employment, in RPI and stuff like that, then we would have to basically go through the VAR equation results. Okay, I have to click here, and when we visualize the whole model, okay, you see we have a wealth of data, which is very interesting. And because you all see that the ARIMA forecast model is not very precise for each time series, you need to do more modeling, and then you say, okay, I want to see the VAR, I want to see if it's goal, if it's offside, and I want to see what is in terms of multilinear autoregression based on vectors, on column vectors of data. I have the machine works through what is the correlation values in matrices form, and each data column is transformed into a vector data column. And so the machine works through the data and does a spectacular econometric model, which is really spectacular. It's something that I like a lot, but it's very, very cumbersome for the machine computational power, even if you have the most advanced CPU and stuff like that. Okay, so I want to see, just out of curiosity, right, okay, yeah, okay, so what are the statistically significant variation results for M4 money supply? So we have a correlation at the first lag with money supply. So money supply, it's correlated to the previous quarter money supply impulse. So you have a response in the following quarter from money supply, in money supply. And here we have at lag 3, so in the previous 3 quarters, if I have a negative shock in RPI, based on the 12 months percentage change of the RPI that tracks rent, I have a negative coefficient for money supply. So inflation is a monetary phenomena, and so it means that if I have less money supply, I'm sorry, I have to explain it better. If in the previous 3 lags I have a negative impulse, I have an impulse from RPI, then I have a negative coefficient in money supply. Okay, money supply has a negative coefficient of -2. Okay, not money supply, but the 3 lag effect of RPI rent generates a -2 coefficient for money supply. So what means that if I have the lagged effect of rents, it's a negative coefficient for money supply. I can presume that, for example, if I have growing rents, it's not for a direct effect of money supply, but probably the money supply ends up in rents for landlords. Okay, or vice versa. If I have a negative lagged effect of rent inflation, I will have a negative effect on money supply, so which is more correlated to the concept of inflation, to money supply of inflation. So what I'm trying to say is that if I have if rents are not growing, if I don't have pressure in the housing market from rents going up, the inflation measure or the housing component, it has a correlation, it has a lagged correlation with money supply. So it means that there is less money supply in the economy. Okay, so there is less disposable income that it's able to absorb a lagged effect of inflation. Okay, so all this mumbo jumbo to say that money supply, it's a determinant factor for housing market inflation, of course. Yeah, so the more money supply, the more house prices and rent prices go up. So if I have a negative lag effect on house costs, I will have a negative effect on money supply. Okay, so the inflation problem of the housing costs, which is a big component of the inflation problem in the UK, is directly correlated to the money supply. Okay, so from my point of view, the data point is very important for me, because if you manage to achieve an economic policy which is able to stabilize rent prices, you will have a containment effect on inflation, and then you will have a positive effect on the value of money, not on the money supply. So you will not need to print out money, because the pound that you will have in your pocket will be much more valuable. Okay, because you don't have money supply, not that you don't have money, but the value, the purchasing power of money will be higher. And to achieve this objective, you need to have an economic policy and a fiscal policy which are able to stabilize the big problem in UK economy, which is the housing market and the rental market, which is the housing crisis. I have to build more houses, but if you build more houses and the houses you put on the market, they are marked to market at a higher price, an inflated price, you are not solving anything. You are only basically producing more and more problems. You are exacerbating the problem. Okay, that's my humble opinion. And okay, so let's see here. Okay, bang. Okay, so money supply, of course, it's directly correlated to the Bank of England bank rate. So the Bank of England bank rate has a 3-lag negative effect on money supply. So if the Bank of England hikes interest rate, it has a very large coefficient negative lag effect on money supply. Okay, which is typical of monetary policy transmission mechanism. Okay, and here we have a lag 5 of the M4 growth rate. So if the M4 money supply growth rate, it has 5 lag effect on money supply. Okay, so if you have monetary stimulus, even 5 quarters later, you will have a positive effect on money supply, because probably there is more credit in the economy, banks are giving more credit, so forth and so on. So that's the beauty of a VAR model. So of course, what are significant are only the lagged effect, which are statistically significant, and then you basically those are visual in the charts. Then you have the impulse response function from the VAR model. And yeah, so it's been a huge pleasure to be with you all. And again, just thumbs up for me, a big like, subscribe, and I will see you in the next video. Leave a comment, subscribe, and yes, thanks a lot. See you in the next video.